Hello, my name is Whitney. This is my final project presentation for ECE 591. My project was on the Kaggle competition hosted by Novozymes Enzyme Stability Predictions. So, first of all, what exactly are enzymes? And also, why do we care about their stability? So, enzymes are proteins that act as catalysts in the chemical reactions of living organisms. Virtually every process in the natural world involves proteins in some shape or form. However, working with proteins can be difficult, as they can be very fragile and also very sensitive to temperature. This sensitivity, called thermostability, is vital information for biological engineers, because many enzymes are only marginally stable, which limits their performance under harsh application conditions. It is more efficient to develop computational approaches to predict their stability than simply trying to produce them in the lab first. So, the goal of this project was to develop a machine learning based natural language model to predict and rank the enzyme's thermostability. Now, we'll take a bit of time to talk about why we're using natural language processing to do this, as well as talk a little bit about what other methods we have at our disposal. And also we will talk about how well we managed to succeed in this goal. So, why natural language processing? And it certainly wasn't intuitive to me when I first started looking at this problem. After all, how could an enzyme sequence have anything to do with a natural language? Well, enzymes can be sequenced. In short, a protein can be put into a fancy box, like the one pictured, and you're returned with a long string of data that describes the amino acids that make up the enzyme. While not what you might think of as language per se, there is still a pattern to extract from that data. This is currently one of the most common ways that information about proteins is obtained. But what about other options? After all, a protein's function is largely dictated by its physical structure, and it would seem more intuitive to base your models off of the physical structure, not just the sequence. Well, the physical structure of a protein is obtained using crystallography. Basically, your structure is held in place and bombarded with X-rays. These X-rays diffract around the various structures, and that is projected onto an imaging sensor, which then in turn is able to be reconstructed to eventually recreate what the physical structure of these proteins looks like. And it actually can work pretty well. As you can see here, this is a immune signal interleukin, number 12, which is the blue bit there, which has been being bound to its receptor. And this seems great. We have a method to determine what the structure of the protein is, and we can use this data to train some other models, right? Well, in theory, this is correct. However, there is still a bit of a major issue with that currently is proving difficult to deal with. Remember how I said that the sequencing was the main way that protein information was gathered? The reason for that is because it now has become incredibly cheap to do that, and it's also very fast. And according to the NCBI-NR database, which is one of the larger databases available with this sequence data, they have almost 8 million protein sequences, with an additional 2.6 billion residual sequenced. In comparison, There's only a few thousand physical structures known. According to Nature, the Worldwide Protein Data Bank contains about 65,000 entries. The problem is that in order to be able to actually image that protein, they must be crystallized. This process of crystallization is extremely difficult, and it can take multiple weeks, if not months, to get a single protein to crystallize. Now, at this point, I think the problem is becoming apparent. Machine learning models require massive amounts of data. A prime example is the image diffusion model DALL-E 2. DALL-E 2 was trained on about 400 million text-image pairs, and a scant 65,000 structures is very difficult to develop a usable model from. Now, there is being some work done in that area, specifically with AlphaFold. However, this testing is probably going to be required. More testing is going to be required before that's fully accepted as a valid alternative to this. So back to our particular problem that we were working on. What's pictured here is a small section of the data that was provided for this competition. There are a few things that kind of want to really sort of point out and explain. The sort of random string of letters is specifically the sequence of amino acids, as well as then Tm on the side, which is your specific melting temperature, and then pH as well, pH. And so for my approach to this, I decided that I wanted to utilize a LSTM to try and model the language, if you will, of these particular amino sequences. So this is the structure of my model. This was, luckily I had some code available on Kaggle to handle some of the data processing and everything else, because that's always a joy. But the data was separated into two separate groups. So one was just looking at that pH value, which is going to input 16. And then the other one was the actual sequence data. And then again, both of these are validating against your temperature data here. So starting with input on the left side here, that sequence data goes down and is then passed through an embedding layer and then is passed on to a 16-layer LSTM. And then this is then passed on to a 8-layer dense network, which is utilizing a dropout with a 0.2 rate, and then moves on to a 4-layer LSTM. And from the other side, that pH that was just fed into a dense layer, and then both of those streams were batch normalized in concatenator before continuing on to be passed through to more dense layers. And unfortunately, I flew a little bit too close to the sun with this. I messed around with it a little too long and a little too, well, up to the deadline. And so it was working pretty well, but then I futzed with it too much and it ended up breaking a little bit, but I think in the end it ended up working out pretty well. This is a sample of the data set, sort of the actual versus the predicted. And I think that this sort of shows that it's definitely very promising. We'd like that to be a little bit more on the 45 angle, but there is a pretty good correlation that it's definitely was heading in the right direction. And this is a project I've actually really been enjoying working on, and I think I'm probably going to continue going with. It's certainly an interesting problem to undertake. And so I think for sort of future improvements, I think going back and taking another look at the that sort of first portion of that, which is sort of getting that more heavily training on the actual sort of language processing of it and actually trying to recognize those patterns a little bit more uniquely, not necessarily correlated to the melting temperature, but just sort of within itself, which ones are just sort of coming up more often. and more frequently, and getting that sort of trained first, and then actually, freezing that and then more fully doing the back end of that, where it would continue on and actually start correlating to the melting temperature of it. But I will say again, I was feeling I'm pretty happy overall with my progress here. I think I was feeling a little bit down on myself because I was checking against the scoreboard on Kaggle, and then I realized that the guy that was at the top of the board was technically a machine learning researcher for NVIDIA. So, I guess if you're going to get beat, that's a pretty good way to get beat. But thank you very much for watching, and thank you for a good semester.